Good morning, good afternoon, good evening to all, and welcome to this month's community of practice on breeding scheme optimization. My name is Adam Asei. I am a quantitative geneticist based in Nairobi and one of the more recent members of the Accelerate Breeding team. I have the pleasure and privilege to moderate our meeting today on behalf of Dr. Dorcas Gemenet, who is currently in transit from the African Plant Breeders Association conference and unfortunately could not lead our COP today. It is a real pleasure to me to be here with you all. Our speaker today is Lorena Batista. Many of you may already know her. She is one of our quantitative geneticists in the Accelerate Breeding team. She joined the team about 2 years ago and has contributed extensively to work with the RTB crops. She's currently focusing on the development and optimization of BioFlow, our breeding data analytics pipeline, which many of you are already familiar with. Today, Lorena will tackle a key concept in breeding program optimization, heritability. It's a topic that underpins how we interpret data and make selection decisions. Lorena will guide us through this concept from a breeder perspective, shedding light on some critical elements that can shape decision-making in the field. We are very excited to have her with us today. Lorena, thank you very much for presenting this important topic. The floor is yours.
All right, thank you, Adama. I have my camera on right now just so you all can see my face. But yes, I think you gave a very good introduction. So it's like I'm just basically gonna skip the first slide and go straight to the presentation. So yes, just to say hello again, my name is Lorena Batista, quantitative geneticist. And yes, I work for the Accelerate team and mostly involved in bioflow activities. So I'm gonna turn off my camera now so my internet connection does not disrupt anything. And there you go. Starting the presentation now. Let me see. Yes. So this is basically a summary of my presentation, and I'd like to begin this by giving you what's the idea behind today's presentation and like how we came to be. It came from a meeting I had with my colleagues in the Accelerate team. We were trying to brainstorm around which metrics we should be adding to Bioflow. And when we started discussing heritability, we realized there's many different formulas and many different nomenclatures. So I thought it would be useful to the community to have a talk about this. I'm hoping to start a discussion here. So these are my gathered thoughts, like this whole presentation. Summarizes like what I came to understand as heritability, and this is kind of like on a way a personal journey here, and I really hope that a lot of it resonates to you. So basically, I'm going to start by explaining what coefficient of determination is. I'm going to give a very general definition of heritability. Then I'm going to show you the different heritability metrics, some common misconceptions about the concept of heritability, and at the end, I'll summarize and give you some practical tips as well. So now let's get started. And if I want to start a broad definition of heritability, I will make sure that everyone understands what a coefficient of determination is. I have the scatter plot here showing the values for variables x and y. And let's assume y is the variable we're trying to understand, and x is the variable I want to use to try and understand y. The dashed green line is the overall mean of y, And if I ignore x, this dimension over here doesn't exist. It's like all these points are collapsed into this axis. And I can only explain y based in its general mean. So all predictions of y would take the value of the mean of y. But if I regress y on x, I'll now have predictions on y for each value of x. So in pink, here I have my regression line, and the pink dots are representing the predictions that I have from this regression. I'm going to start like putting some formulas here. So like these three little lines here are the glossary for each formula element I'm going to be showing. So basically the black dots, as I mentioned, they are representing the values of y, and represented by y with this index I over here. The mean of y represented by y with the dash above it, and the predictions informed by x, which is y with this little hat over here. And now, first I want to represent the total deviation from the mean from each observation of y. And this is what the black dashed lines are representing over here. If I now take into account my linear regression, I can rewrite this total deviation into two different components. The blue dashed lines are showing the difference between my predictions and the overall means. And if you think about the overall mean as how the predictions were before I added information from X, then these blue dashed lines are just highlighting how my information, how my predictions changed after I included information from X. So basically, is what the model made, the shift that the model made away from the mean. And this regression, however, does not explain entirely the total deviation from the mean. So I still have some differences between the model predictions and the observed values of y. So it's my leftover error, and I'm going to be calling this leftover error the residual, and the blue portion over here, which is the portion that is explained by the model, by my linear regression. If I sum these values across all the observations, and I'll need to do this through the sum of squares so they don't cancel each other out, I'll have that the total sum of squares is equal to the explained sum of squares plus the residual sum of squares. And I can define my coefficient of determination of this regression by this formula, which is 1 minus the residual sum of squares divided by the total sum of squares. So what's the intuition behind all these formulas that I'm showing here? Basically, if the linear model doesn't explain anything beyond the mean, so it's basically like equal to the green dashed line in the plot over here. So it's like all the blue part is actually equal to 0. And then I'll have the residual equal the total variation. If they are equal, my coefficient of determination is going to be 0. But alternatively, on the opposite end, if the linear model fully explains the deviation from the mean, all I have is the blue. I'll have no residuals, and the coefficient of determination will be 1. In this particular case, if I have a single prediction, then I'm just using like ordinary least squares, I can actually equate this coefficient of determination to the square correlation between the variables x and y. And this is going to be like, I'm going to tie this in with the concept of heritability later on as well. So it's like, remember this property as well. So now, what does this have like been talking about so far? It seems like just like a regression theory, but what does this have to do with heritability? Let's try and redefine x and y now. And y now becomes my true genetic signal. and the values of X, the estimator of prediction I am using for selection. So we end up with what I consider the broadest definition of heritability you can find, which is the coefficient of determination of a linear regression of the true genetic signal on the value being used for selection. So in other words, how much the estimator of prediction you're using for selection is actually capturing the true genetic signal. Remember that I also defined the coefficient of determination in this case as the square correlation between X and Y. And it's like if renaming these variables, if I'm now using like the values of X as the estimator of prediction, I am using for selection, the correlation of this with the true genetic signal, many of you maybe probably already figured that this is known as the accuracy. So it's also the squared of the accuracy. And just wanted to highlight that despite these two estimates, they are that tightly linked, generally the heritability is interpreted in a completely different way. The accuracy. I'll get to that when I talk about the common conceptual heritability, but I just wanted to highlight this now in the presentation. But now on to link the coefficient of determination with known heritability forms. So with a very simple illustration, only two genotypes, just to not make my slide very crowded, and only two phenotypic observations per genotype. If I didn't have the genotype information, like I've shown before, I will be relying on the overall mean of all white black dots. But with the genotype information, I replace this overall mean with the mean that I obtained for each genotype. So using the same logic from before and luckily the same color code as well, I can say that in blue I have a dashed line, which is the difference from the overall mean by adding the genotype information. Because now from the overall mean, I move this value to the mean of each genotype. And the residual is now the non-genetic noise around the genotype mean. So the difference that I have on my phenotypic observation within each group from the group of the mean of the group. So this is more classical, right? Like you can identify that the phenotypic observation is equal to the overall mean plus this genotype effect and the residual. And I use the coefficient of determination formula. I'll now I can now try and rewrite this formula based on the terms of this model. So I can say that the total variation that I have is my total phenotypic variation, the residual variation, I'm calling sigma square E. And eventually, if I plug in these values in the coefficient of determination formula, I'll eventually get to this formula here. And I'm hoping many of you already recognize this as the broad sense heritability formula. Summary so far. Then what I want to highlight the most is the heritability as the coefficient of determination of a linear regression of the true genetic signal on the value being used for selection. So before we choose the heritability metrics that is relevant for us, we need to think about what is the true genetic signal that I'm trying to capture and what is the value that I am using for selection. And depending on these two quantities, the formula for the heritability is going to change. The first case is when I change the values I am selecting on. And I think the plot level heritability and the entry mean level heritability are a good way of illustrating what a change in the value can do to the heritability formula, basically. So now here at the plot level, I am showing 4 phenotypic measurements of the same genotype, and the red dashed lines represent the difference between the true genetic mean and the observed, like my phenotype values. If I am selecting based on the individual plots, basically, I am subject to more residual variation, as you can see here, than if I perform my selection based on the average across replicates. Think of each residual as a little or large up and down push. And if I have several independent pushes, some of them will cancel each other out. So the average push is actually smaller than any individual push. So if I am performing selection based on the entry means, the residuals, they are going to shrink by a factor of 1 of the number of replicates. And the formula for entry mean heritability will then reflect that. So the residual here is now divided by the number of replicates. And the same logic applies if you're doing selection, the average across locations. This formula, both like the entry mean heritability, you might also see it being referred as repeatability in the literature as well. So now let's think about which values I am trying to target and like when they change. And I think the broad sense heritability and the narrow sense heritability are a good way of illustrating when I change the true genetic signal I'm trying to capture. So if I'm trying to capture the total genetic value with my selection, the broad sense heritability is the metrics that's going to tell me about how effectively I am performing this selection. But if instead I'm trying to capture breeding values with my selection, the narrow sense heritability is the metric that's relevant instead. So generally, you're interested in total genetic value when you're selecting for advancement, for advancing material across stages in the breeding program. And you're interested in the breeding values if you're trying to make selection for the parents, right? So the different contexts in the breeding programs, they will require different metrics of heritability as well. Unless, if you're using mixed models to estimate the blobs, be it, I would say, like with genomic information, without genomic information, pedigree information, if you're using blobs for your selection, especially if you have unbalanced data, we have to talk about reliability and current heritability. If you're making selection based on blobs, reliability and current heritability are the relevant metrics of heritability that you should be considering. So basically, for like to give an intuition about reliability, every blob will come with an estimate of the prediction error variance for that blob. And what the prediction error variance will tell you is about the amount of uncertainty surrounding each of your blobs. So I try to illustrate this in the figure. So these are the genotypes ranked by blob, and these are the blob values. And each blue circle, it's the size is proportional to the amount of prediction error variance that you have. So if you have, let's say, very little prediction error variance, these bars over here, the vertical gray bars, they indicate the amount of uncertainty that you have on a blob estimate. So it's like this large circle indicates that the prediction error variance is actually small, and I have more certainty on this estimate. And if the circle is little, it indicates that I have a really high prediction error variance and a lot of uncertainty around this estimate. And the gist here is that if I have a lot of uncertainty around my blob estimates, it becomes difficult to differentiate between the genotypes with confidence. So what the reliability formula does is like it averages the prediction variance across your blob estimates, and what is going to tell you value of reliability is basically how the true genetic value is determined by the blob rather than noise. Basically, how well your blobs are capturing the genetic signal rather than noise. Alternatively, you can also consider that you are making selection decisions based on the ranking of the genotypes obtained with the blobs, meaning that you are comparing a genotype with the other ones, and then you're using this to make a rank. So the better you can differentiate between two genotypes, the more accurate your ranking is going to be, right? So in this case, you can also evaluate the standard error of the differences between the genotypes, because what it does is it measures the uncertainty within each comparison. So the smaller the standard error of the differences, the more I trust the differences that I observe between my blobs. So in the plot, the red bars here, they indicate the standard error of the differences for four different pair of genotypes. So looking at the standard errors, these two here have smaller standard errors of the differences than these two contrasts here. So what this means is that I can probably trust these two contrasts more than these two. Like these differences that I am observing are more likely due to true genetic signal. So the Cullis heritability is based on these standard errors. So it averages out the standard errors across all comparisons to tell you on average how determined are your genotype contrasts by genetics rather than noise. And the reason I'm putting these two metrics is because I've seen them being used interchangeably. So it's like Cullis heritability and reliability. And even I had a confusion about these terms. So I decided to add this distinction here. So yeah, maybe this could help someone to help differentiate the two as well. And as I mentioned before, people often associate accuracy with experimental quality and how much noise is in a selection value. And there is this general misconception that heritability values are telling a completely different story, which is much more related to some kind of true biological meaning. So it's like how much of a trait is determined by genetics, whether a trait is determined by genes or not, how many genes are controlling this trait. They think it is a fixed value, or it gives you some information about the architecture of the trait. And what I wanted to highlight, this is why it's like in a big, giant orange box, is that heritability is not an intrinsic property of the trait. Heritability values are a coefficient of determination on a linear regression, so they are really tied to the data set. So this population, this environmental set, this specific experimental design that you used, and the model that you used to evaluate it. Change any of those, and the value of the heritability is going to change. A high heritability or low heritability does not tell you directly about how much the trait is determined by genetics or not, but rather like a high heritability means given this data and this model you use to evaluate the trait, a large share of the variance in the selection value that you're using, it can be attributed to genetic effects. A low heritability, it can be tied to low genetic diversity, but it also often means that there's a lot of measurement noise and poor experimental control. And also, both accuracy and heritability are telling you about how much of what you care about is determined by the values that you're using for selection. Basically, you can think of it as a measurement of how effectively you are performing your selection. So what do I do when my heritability is low? I just put here like a quick sheet. You can, I hope Julie is going to share this presentation with you or afterwards. So it's like you can go back to here and like just try and like make sense of these steps, but just briefly like check the genetic variance in your breeding population. So if your genetic variance is super low, even in like a very small residual variance is going to lower your heritability estimates considerably. You can also check the literature on the same trait and crop just to see if this low value of heritability that you got is actually could be expected for your case. So like check the heritability ranges on papers that use papers or reports that use approximately the same level of replication, and try and gather information about the genetic architecture of the trait as well. So more complex traits, they'll tend to towards lower heritabilities because they are highly influenced by the environment. So the phenotype changes considerably depending on the conditions that the plant is submitted to. After that, check your data as well. Like look for data integrity, the amount of missingness that you have in your data, and if the measurements that you have are actually consistent with the biology of the trait as well. So you might have a lot of wrong measurements over there that are lowering your accuracy. You can also check your experiment or have a biometrician do so for you. But was your experimental, like check if your experimental design was adequate? How were the environmental conditions in that particular experiment that got low heritability? If all the plants were submitted to high stress, it's much more difficult to differentiate between them. Can you improve field management practices, just like how you conduct your experiment, how your measurements are taken as well? Can I do this more accurately? Can you add locations if you have a lot of GBI on your data set? And also check your model or have a biometrician or quantitative geneticist do so for you, but do the residuals look okay? Can you model spatial variation, the residuals? Can you add covariates? You can add markers for genomic selection. You can add environmental covariates as well to try and improve these heritability estimates as well. So in a nutshell, what I wanted to, basically, the message that I wanted to give with this presentation is that which heritability metrics is relevant to you. It was going to be fully dependent on the context. You should always think about what is your selection unit, what is the estimator or prediction that you're using for selection, and what is the true value that you're trying to target when selecting. Once you figure these questions out, the heritability, much like the accuracy, should give you information of how effectively you are performing your selection. Yeah, with this, I reached the end of the presentation. If any of you want to reach out, this is my email, and I am open to questions from the audience.
Thank you, Lorena, for this brilliant presentation. Is there any question or comment from the audience?
Yeah, can I come in?
Yes, Dominic.
Yeah,
Go
this is
Oh,
Mr.
thank you for your presentation. Yeah, you were so fast, so we didn't capture some of the things. So I would wish that maybe we find a way how we can get the presentation. And then also I didn't capture her email. I wanted to get that. Thank you.
Yes, maybe I think all the presentations are going to be made available on YouTube afterwards. So it's like you can catch that on that. I am sorry for the flow of the presentation. Maybe I should have spoken a little bit slower, but if there are any points that you want me to go back to, we have quite a bit of time. So it's like I'll gladly return to some of the slides.
Can I come in?
Just,
yeah. I have two questions. One would be a little longer. The other one is a short one. The first one was that you were mentioning about narrow sense heritability and in broad sense heritability, and using give me at least what I would say that enough explanations how we can interpret those narrow sense and broad sense heritability. The second one is that you were making the comparisons among within the bloop which statistical packages that could be used to do those comparisons?
Like the first thing is like I cannot hear you very well. Like your voice seems very far away to me. I think there's something to do with my headphones because everybody's voice is a little bit far away today. But just try and go back to the broad narrow sensitivity. Maybe Ada, if you could like summarize the question for me.
This is the one that indeed, this is the slide that I was asking about. That which
Okay, this
statistical
one,
package,
the
yeah, which
standard error, the
statistical package,
differences.
yeah, which statistical package that you are using to make those comparisons?
Oh, this, especially these, like you can get these standard error, the differences through a grammar. Even like this is one of the outputs of the predict function. So yeah, like you can get the standard of the differences of the data as well, but also like any package that will give you the coefficient matrix of the mixed model equations should also provide you with the reliability. I cannot, for the love, yeah. These slides are passing really weirdly. I don't know if it's my computer, but I lost control of my own presentation. Oh, there you go. Yes, so for the reliability as well, you can get the prediction error variances. This is the diagonal of the coefficient matrix of the mixed model equations. So it's like any package that will give you this coefficient matrix as well, the inverse of it. You can extract the PEVs. But I hope this was helpful. And about, like you had a question about the narrow and broad sense heritability, if you can repeat that as well.
Yeah, you were talking about the broad sense heritabilities for advancements, narrow sense for selection of parents, but you didn't give
Yes.
why so, the enough
Okay.
information.
Yeah, it's sorry. Like maybe I spoke really fast. Like my intention is to actually explain this. It's just because the true value here in this case for the broad sense heritability is the total genetic value. So this includes both the additive part and dominance and maybe more epistatic effects. Yeah, like the majority of the non-additive effects, they are actually non-heritable, right? So it's like if I use them for selection of parents, is actually like a lot of this variation is not going to be passed on towards the next cycle. But for advancement, I'm basically like just taking the same material and evaluated in further stages. And I'm interested in its performance as a variety as well. It's the performance of the offspring after I use this material for crossing afterwards. So in this case, for advancement, it's more relevant that you capture the total variation of your trait. But when we talk about the selection of parents, we're actually more interested in the portion of the variation that is actually heritable, which is basically the additive portion of the variance. So it's like it relates to the additive value. That's what you're trying to capture when you're using it for selection of parents. So then the narrow sense heritability becomes more relevant in this type of selection. And it's going to tell you how effectively you are selecting for parents. Does that answer your question?
Yeah, thank you.
No worries.
That's clear. Lorena, we have two questions. We have two questions in the chat. So first, Dr. Meseka, heritability under stress condition is always low for grain yield. How do you explain this in terms of genetics, experimental design, and model use for analysis?
Yes. So basically, if you have a field and all your genotypes are completely stressed, in terms of genetics, it's like the true genetic potential of the plants that you have in the field is not actually being expressed because like basically like everybody's going to have terrible yields, right? So it's like if there were genetic differences, these are not being expressed on your phenotypic value. The experimental design, like there's not a lot that you can do if all your field is basically bad, but if you expect some parts of your field to be more affected by stress than the others, what you could do is either try and model, like do some spatial analysis in your residuals, or try to set up your experimental design to account for this heterogeneity in the field as well. And it should increase your heritability. But if your entire field is badly affected by stress, all your plants are going to be performing poorly, regardless of genetic potential. So whatever you're selecting on is not like reflecting any of the true genetic value over here, like even if you use a really good model. So yeah.
Perfect. Just to alternate, we have two other questions on the chat, but let's give the floor to PG, who's asking.
Yes, thank you
PG,
very
yes.
much.
Yeah.
Yes, I didn't change my name on there, but it's Paul Gibson. And thank you very much for a very clear presentation and a lot of very good information. In a practical application, I find that PEV and SED reflect the assumptions that are made in the different packages for analysis. And I've found different assumptions are being made in different R packages, therefore giving different results, especially how G by E enters into those calculations and how to control that, because the default assumptions are not necessarily what we need in many of our experiments. And so I'm still exploring how can I instruct students and make it simple enough and yet accurate on how they're handling G by E, for example. Do you have suggestions?
So I think if I understand you well, the main suggestion that I can give as I'm trying to like keep the theme of this presentation is that you really should think about what you're selecting on and what you're trying to target, right? So in the case of the PEV, it's really important that you can as well what are your predictors. So like you might have to multiply basically the PV matrix, pre and post multiply by the specific contrast that you are using for your predictors. So let's say that, yeah, it's like you really need to get the prediction or variance of the value that you're using for selection. Sometimes it's purely the blob, but it could be like the blob plus the intercept, and this kind of changes the prediction errors over there as well, and therefore it's going to change the heritability value. So yes, like pay attention. That's like my main tip as well. Like really pay attention to what you're estimating and see if the outputs from these models are actually reflecting that.
If I may follow up, a big portion of my problem is that the easily available explanatory material doesn't specify exactly which terms are affecting that prediction. And maybe there's a way to output that, but I'm fairly novice in R and I haven't been able to identify how to output what is actually going into that prediction.
Yeah, it's like it's difficult to comment because like it's like I will need to look into like each package like to see what are the predictions actually like based on. And yeah, it's just like I'll need to look into detail like what each package is doing, and I try and like tailor it to the right formula. But yeah, it's unfortunate that that's like the material is not very clear as well. I'm hoping at least like AES-REM, or like you can get some level of support from the company VSNI, like to try and get to the bottom of this. But yeah, like I don't have, I would say, practical tips for any specific package. It's like I generally, when I'm running an analysis, I do it on a case-by-case basis. What I try to do is I get the coefficient matrix of the mixed model equations, and I try to figure out how I obtain my predictions as well. So it's like generally I have a bit of control over that, because like there's going to be an estimate of an intercept. So it's like I try to have the intercept very explicitly in the model. And if I add to that, like I know that my I know exactly which terms are comprising the predictions that I'm trying to make for the material I am evaluating. And with this, like I can tie the link with the prediction error variance matrix. But yes, like you really need to be fully aware of what's embedded on the predictions that you're working with.
Thank you very much. The coefficient matrix will be a help, and I haven't been outputting those. But any other information you find about how to see what model is actually being used, what assumptions are about fixed and random effects and such, I'd be very glad to be informed of anything helpful you find.
Okay, will do.
Gr-
Feel free
Great.
to reach me out as well. I can send an email.
Perfect. Thank you very much, Paul, for this interesting question and discussion. So the next question in the chat is from Danielle. Danielle said, thanks for the presentation. Could you comment on accounting for population structure when calculating heritability?
Yeah, it's like with this presentation, it's like I try to give like just a very overall understanding. Generally, like you can add a lot of things. I would say to like basically like a population structure. You can either add, I don't know, maybe like your PCA results as covariates in the model, or there's different ways of adding it, as like you can plug in the kinship matrix on the mixed model equations, or there's like different ways of like plugging in the population structure in the mixed model equations. I don't think there's anything specifically tying it to the metrics of heritability specifically, but if accounting for population structure is gonna make your blobs more accurate, it's gonna be reflecting on if you're using mixed model equations, like you should actually be looking into reliability, occurrence, heritability, and it should improve how much of the true genetic signal your blobs are capturing. So that's my only comment over here.
Great, thank you. There is another comment from Mulugeta. So thank you, Lorena, for the wonderful presentation. I have a question. What can we do if the heritability is consistently low, even after checking all those factors that could have suspected to contribute it for the low heritability?
Yeah, I'm gonna go back
Uh,
to that slide. because these are quite a lot of factors. So let's say that you check and your genetic variance is actually okay, like you have quite a lot of genetic diversity among your population. And yes, this is the check on the literature. So it's like if constantly on the literature you observe higher heritability ranges for the trait you're trying to evaluate. And like basically like using a very similar experimental setup as you're using. And if you check the genetic architecture of the traits, like first you need to set up your expectations as well. It's like you could be getting a low heritability because that's how the trait behaves. And it's like there's gonna be very little you can do. You could still try and improve your experiment and model, but like there's a limitations, like you might not get super high heritability. But I find like even if you look at the formula for the entry mean heritability, for example, if you use a lot of replication, your residual is divided by it, and it's going to shrink considerably, and you're going to have at least a high estimate of repeatability, for example. So it's like I find it very unlikely that if you improve all of these factors, it's like if you like if your data is okay, but like if you really improve your experimental designs more specifically, then you would still be getting low heritabilities regardless, right? It's like then yeah, there's got to be something wrong, either with like the management practices or the measurements, like how they are being taken. But if you increase the amount of replication, like it could be across locations, or just like replicate more. It's this kind of like brute forcing a high heritability, and you can actually brute force it, but like you need to invest resources into it.
Great. Thank you for this question and answer, Lorena. It's very clear. Is there any other comment? I don't see any other comment in the chat, and I don't see a hand. We still have 10 minutes.
Yeah,
So,
like if people like still have that as well, use my email, they just write it down. Don't hesitate and reach out to me. Again, for speaking quickly, maybe I should have slowed down in a lot of the explanations, but hopefully like you guys will be able to see this presentation as well on YouTube. You can put it on a 0.5 speed and like watch it more slowly as well. And yeah, probably like rewatching it, a lot of these concepts will stick. And yes, thank you for the massive presence. I see there's like 72 participants. I'm really happy with the attendance.
yes, thank you again, Lorena. Thank you very much for such a clear and insightful presentation. And thank you all for the rich exchange and discussion. So it was a success. We have reached more than 80 connections. So thank you again. Have a good day. Bye.